I want to first finish what we left off last time, and then we'll stop a little bit for some administration issues and announcements and move on. So we talked about VC dimensions. Basically, we looked at ways to quantify generalization. And we gave a few examples. I want to summarize with this example here that you actually already saw, but not completely. So we're looking at hypothesis space of all axis parallel rectangles in the plane. And the question is, can we pack learn it? So let's think again about what we've done with pack learning, and specifically with the case of infinite dimension hypothesis spaces. So in order to determine whether we can pack learn, we need to answer two questions. One is the sample complexity question. And the second one is, can we find an algorithm? And we can also ask whether the algorithm is efficient or not to know whether it's efficiently pack learnable. Thanks. OK, so the first question is VC dimension. And we want to know, we want to address the shattering question. So my claim here is that some, for instance, for sets of 4 points can be shattered. This is an example of a set of 4 points that can be shattered. What does it mean that it can be shattered? Again, so by the way, there were very good questions on this on Piazza. What would be even better from your perspective, all of you, is that if you guys try to answer questions that other students ask. It's going to be good for them because you'll answer the questions. It's going to be good for you because you'll practice putting together an argument that answers the question. And it will be good for us as the teachers and TAs because it will let us know whether you understand, and if you don't, what don't you understand. It's the best thing for us to see you trying to explain something in order to gauge into what you understand and what you don't. So please don't be shy. Try to answer other students' questions. Ask questions, and this will give us a better idea. Back to this. So what does it mean that we can shatter? Shatter is a notion of a set, right? So given a set of points, can we shatter it? So here is a set of points. Shattering it means that using this collection of hypotheses, rectangles in the real plane, means that for each labeling of these 4 points, which means each of the 16 labelings, I can find a hypothesis that agrees with the labeling, right? So I need to consider 16 different axis parallel rectangle. And I'm going to invent an axis parallel rectangle in order to shatter a given configuration, in order to be consistent with an existing configuration. So if you want all these to be positive, you can find this rectangle here. If you want all this to be negative, you'll put a rectangle here. If you want this one to be positive and the rest negative, you'll put a rectangle here, and so on and so forth. And you can convince yourself easily that this set of 4 points can be shattered. Agreed? Questions? Now it's true that not all sets of 4 points can be shattered. But it doesn't matter. It's sufficient for me to show that there is one set of size 4 that can be shattered to already argue that the VC dimension of this hypothesis space is greater or equal to 4. OK? So there are some subtleties in the definition You really have to sit down and kind of read it carefully, make sure you understand. This point is clear? Next is I have to go beyond 4. Next we're going to go to 5, and I'm going to argue that no set of 5 points can be shattered. An argument. Why is that the case? Yeah. Okay, so we can take these 5 points, this set, and say, let's find the extreme points. What are the extreme points here? Along the x-axis, I'm going to take the minimum and the maximum. Along the y-axis, I'm going to take the minimum and the maximum. And then what could happen? It could be that all 5 will be on this extreme, which means there are going to be 2 points that agree. Or it could be that 4 are going to be there, and 1 is going to be in the middle, right? Either way, what will I do? What do I need to know to show in order to show that this specific set cannot be shattered?
Label the extreme points as the positive and the inner one as the negative.
Right. So I need to show that there is one labeling that is inconsistent with any member of my hypothesis space. You cannot find an axis parallel rectangle. Axis parallel rectangle, our understanding is that inside it's positive, outside it's negative. So you need to show me one labeling of these 5 points, and there are 32 labelings, so you may need to work hard, even though in this case it's quite intuitive. You need to show me that for this labeling there is no axis parallel rectangle that agrees with this. And indeed, if you choose this, because there are at most 4 distinct extreme points, I cannot include those that are on the extremes as positive and the one internal is negative. Or if you want, if there's no internal, another one on the same side as positive. Okay, so what we've shown is that VC dimension is 4, right? It's greater than equal to 4 because of the previous argument. It's strictly less than 5 because of this argument, so it's equal 4. From a sample complexity perspective, we have pack learnability. The next thing is algorithm. Yes?
What about the case for, what is the argument for the case where all 5 points are on the rectangle?
Same thing. So I'm going to color 4 of them as positive and the 5th as negative. So there's no axis parallel rectangle that can do this. Okay, so so now we need to give an algorithm. Yeah.
Does the axis parallel rectangle necessarily have the positives inside it? Can't it have the opposite?
So do whatever. Oh, you want negative inside and positive outside. I defined it otherwise, but it doesn't matter. You can define it this way also, and it's going to work for the same reason.
Then in the case of 4 and 1, where 4 are lying on the extremes and 1 is inside, can't we just shrink the rectangle by an epsilon and everything outside will be positive? And
So change the labels.
that's what I'm saying. The axis parallel rectangle has a fixed convention of inside being positive or outside.
No. So we have to agree what is the hypothesis space.
Can't we?
Once we cannot have both, right? So if we agree that inside is positive, we have to work accordingly. If we agree that it's another hypothesis space where it's positive outside, we have to work with this. So for this hypothesis space, these 2 hypothesis spaces, this proof holds. Okay, so now we need an algorithm. Algorithm would be simple. We talked about it before. Basically, given a set of points, we can look only in the positive examples, find the smallest rectangle that contains the positive example, which again basically means take the max values on the x and the y, takes the mean values on the x and the y of the positive examples, draw a rectangle that is consistent with this. And this will be your rectangle. Is this the best rectangle that you want to come up with? In real life, if I ask you to learn an axis parallel rectangle from this data set, will this be the rectangle that your algorithm returns? Yeah.
You might want to increase the margin so that it's not so set on positive.
So what would you do specifically?
I mean, I keep a bounding box on the positive examples just like as it is shown in the blue, but I keep a margin beyond that.
How large a margin would you do? You have to write the code, so just write it.
Well, I guess large enough, I guess somewhere around in the middle of the, as in, I can keep increasing the bounding box so that it doesn't touch a negative example, and somewhere in between that.
Right, so you can grow the axis parallel rectangle maybe with the same rate on both x's, both y's, until it reaches the first negative example, and then half the distance. Something like this. So clearly you see that in real life, you know that you may see new points that will be consistent with an axis parallel rectangle, but will be outside the axis parallel rectangle defined solely by the positive examples, right? So the notion of margin here is a very natural one. We're going to talk about it later this week. I just want to make sure that we know that it's a natural notion not only in the context of the specific linear functions that we have talked and will talk about, but actually it's a natural notion in general. Okay, but we proved that axis parallel rectangle, the hypothesis class of axis parallel rectangle is pack learnable, and moreover that it's efficiently pack learnable because we gave an efficient learning algorithm. So that's basically the final example I wanted to give on pack learning. Questions on pack learning, VC dimension? Okay, so before I conclude, I wanted to say one other thing. We actually talked all the time about upper bounds. Basically, we said several statements of the form, if you see these many examples, everything is going to be good. That is, if you are consistent with these many examples in your training data, don't worry about the future. Your hypothesis is going to be good in the future. Or a relaxation of this, if you are doing pretty well, diagnostic form, on the training data, and you've seen at least M examples, we gave a bound on M, then it's going to be OK in the future. The question is also, is this M necessary? Can you say something about if you don't see enough examples, it's not going to be good, right? So a lower bound. And it turns out, and I'm not going to prove anything, is that you can prove also lower bounds. You can say you must see at least these many points, otherwise things are going to be bad. The important thing for you to understand here, and this is a good exercise for you in understanding the pack learning definition, is what does it mean things could be bad? Because pack is a very strict definition, right? That means that there is a distribution on which it could be bad, right? So specifically, then there exists a distribution D and a target function such that if you see less than these many examples, with probability at least delta, the error is going to be bad, right? So it's the inverse of kind of the strict pack hypothesis. So you could say, I don't care because, it just says that there exists a distribution and there exists a bad function in my class. But it's important to know that, there are some kind of boundary within which you can play, because in principle, you don't know what is the distribution that you're going to see in life, and you don't know what's going to be the hidden function that you're after. Okay, so just wanted to mention there is sample complexity, and I want to summarize what we've done. So we talked about computational learning theory. The key thing was to understand PEC framework. The idea is that we wanted to develop a model that allows us to analyze the effectiveness of learning algorithms. So a learning algorithm should be analyzed not only in terms of, okay, here is some data, we ran the learning algorithm, we got good results, because tomorrow you may get another data set. Can you say something more general about generalization? We talked about sample complexity, and we quantified it in multiple ways. All of them have the same flavor. We talked about consistent learners, and we talked about agnostic learners. We quantified it for a finite hypothesis space, and we saw that the size of the hypothesis space, or the log size of the hypothesis space, is the most important factor here. And then we generalized it to the infinite case and show that the VC dimension is the important factor. In case where sample complexity is okay, we also talked about computational complexity. Can we find this consistent or almost consistent hypothesis efficiently? And showed that these are independent issues, right? It could be that sample complexity is good, computational complexity isn't good. You just don't have an efficient algorithm to do this. And we use this also as a way to revisit again the importance of representation, right? So it could be that it's hard to find a hypothesis if you insist to represent it this way, but if you represent it other ways, the same hypothesis, the same function, you can find it efficiently. Which shouldn't be surprising for you at this point, that representations are important. Okay, so essentially this gave us a way to think about generalization. There's a lot of other things one can study, and people have studied in this context of computational learning theory, and I'm kind of listing a few of them. So we didn't talk about learning with noisy data. We talked about it a little bit in the online context. It can be studied in the context of PEC learning. We actually talked about the notion of specific distribution and highlighted the fact that it's important in PEC learning that you are distribution free. But if you must, or if you want to write a paper, you can also study specific distribution and show PEC learnability on specific distribution. You can think about other representation. Everything we talked about today are really deterministic classes of functions. You can think about probabilistic representation and study PEC learnability there. You can think about neural networks. I talked a little bit about it. Finite automata, I also talked a little bit about it, and I gave the example of different learning protocols. In one learning protocol, learning is hard. In another learning protocol, specifically query-based learning becomes efficient. You can study teaching, and there are many, many other things that I'm not listing here. So if you want to follow up on this theoretical aspect, there's a conference, Computational Learning Theory, that for the last, 20-some years have been studied these kind of questions. One important extension that I'm not going to talk about, but I want to highlight, is a theory that is called PEC Bayesian theory, where the idea is that rather than solely study the distribution-free assumption, saying, there is a distribution, I know nothing about it, all I know is that training and test are governed by the same probability distribution, you can actually relax this assumption and make assumption on the prior distribution over the hypothesis in your hypothesis space. And then you can prove versions of the generalization bounds that we showed here proved the easy ones in this kind of more natural case, where you have some notion of priors, and you can show that everything that makes sense remains sensible there too. Okay. A few final things. So why is it important? So I think that it's actually essential to have some understanding of the theory of what we are doing, rather than just say, oh, look, it works. And hopefully once you kind of get some experience in this area, work in this area, read in this area, you'll also develop this need to be able to characterize in a better way when things work, why things work, when things do not work. So this is really the role of computational learning theory, and I just gave you a small taste into this. Now, one caveat, and we actually mentioned it last time, is that the bounds that we developed here are very, very loose. In fact, as was noted last time, sometimes they are so loose that the probability of something could be larger than 1, right? We just give an upper bound. But nevertheless, it's very important because it gives guidance on model selection. For example, it told us, unless something happens, prefer small hypothesis space over larger hypothesis space. And in a more concrete way, the impact of learning theory was quite significant on a lot of progress in machine learning. And I'm listing here a few of them. Support vector machine that we'll get to next time is one key algorithmic framework that really started with understanding generalization. We know, we talked about it, the notion of sparsity also started with a theoretical questions. Can we learn in a way that only weakly depends on the dimension and more strongly depends on the number of relevant attributes? Boosting, which we're going to talk about now, also started with a theoretical question, specifically a PEC learning question. And all the notion of regularization, understanding regularization, is perhaps the key thing that has happened in machine learning over the last, 30 years. Sort of the move from the standard perceptron that people were able to, at least understood in the 50s, 60s, and stochastic gradient descent that people understood even before, to what's happening today. Maybe a somewhat cynical view, but essentially the only thing that happens is we understand regularization. And we've changed the loss function to include the regularization terms, and that's it. The rest is the same. So really, the key issue was understanding what's important in learning. This is the theoretical step that we've made. Questions? No questions. Okay, so let's move on then to the next step, and this will allow me to break for a second and talk about a couple of things. So I assume you all know homework 4 is due on Thursday. I want to remind you that because we have a midterm next Tuesday and we want to give you the solution this week, so you'll have plenty of time to look at it and understand it, the 96-hour policy is, this week is only going to be 24 hours. So by Friday night, we're going to release the solution. Please, if you cannot do it on time, take up to 24 hours. That's it. 2, midterm exam on next Tuesday. Closed books, which means all you need to bring is yourself and a pencil. There will be a page of formulas in case you need it. You won't need it, I think. You won't even need a calculator. You can bring a calculator if you think that it's this essential. everything that we've covered until this coming Thursday will be in the exam. And I think we already released, if not, we'll release today, a few midterms to give you an idea of what kind of questions we ask. So it's in class. The assumption that we're making is that you can finish it in 75 minutes, or at least most of you can finish it in 75 minutes. And that's it. I'm going to give a review on Thursday. So in addition to the lecture that we're going to have at 12:30, at 6 p.m., we're going to meet here again, and I'm going to give a review. Please come prepared with questions. Otherwise, it will be boring. I'm just going to tell you again what we've done, just very quickly. That's it. Questions? I'm sure many of you have questions about the exam and other things, so that's the time. No questions. Okay. Question.
So basically, like, the question will be only like theoretical ones.
Well, you cannot write programs, right? So we'll ask you, yeah. So, I mean, we could ask you to run an algorithm, but it will be on a small number of examples just to see that you can run it. But yeah, it's pencil and paper, yeah, basically. Okay, just to wrap up, so homework 2 has been released, just that you'll see that you all did very well. A small number of exceptions. If you are an exception, you should probably go and come and talk to me or the TAs to see why you are an exception. But overall, I think everyone did very well. And questions, please go to the TAs if you have any issues with the grading. Okay. Final chance to ask about the exam, any other administrative thing. Okay, so let's move on. So where are we? We talked about a lot of algorithms. We talked about theory. We have a formal notion of learnability now. And we can extend it. We are going to extend it this week in 2 ways, 2 algorithmic ways, or at least build on the theory in 2 algorithmic ways. And today we're going to start with one important algorithmic implication of the theory that is called boosting. So boosting is an algorithm that today is thought about as a general learning paradigms for putting together a strong learner. That's what we want, a strong learner, by putting together a collection of a lot of weak learners. And it actually did not start this way, but this is what boosting is today. And we'll get a little bit to understand what it means. So the original boosting algorithm was actually developed as an answer to a theoretical question in PEC learning. It's a beautiful paper that I really recommend people that are interested in learning to go and read. It's the second paper of Rob Shapiri that I recommend that you read. It's called The Strength of Weak Learnability. It has a lot of other theoretical results beyond just developing the boosting algorithm. But because it was actually developed not as an algorithm, the algorithm that we're going to talk about today is actually different than the original boosting algorithm. It really addresses some interesting theoretical issues and gives some interesting theoretical results. For example, I'm kind of quoting one of the results, the relation between PEC learnability and compression. This is one outcome of the theory of boosting. So specifically, it says something like, if a concept class is efficiently PEC learnable, then it's efficiently PEC learnable by an algorithm whose required memory is bounded by a polynomial in N, C, concept class size, and 1 over epsilon. So essentially, if you can learn, you can compress. Basically, that's what it says, and it quantifies it in a careful way. Moreover, it also says kind of the other direction. It says no concept class. There is no concept class for which efficient pack learnability requires that the entire sample be contained in memory at one time. So it's basically if and only if. You can learn if and only if you can compress. If you can learn and you think that you require all the data to be in memory, you can replace this algorithm by something that forgets most of the data. Okay, so really learning is equivalent to compression in a well-defined way. So anyhow, there are other results, interesting results there. And again, people that are interested should go and look at it. Yes?
And what's the number of features?
It doesn't matter. Oh, n is the number of features, yeah, here. Yeah. Okay, so, but the key contribution of boosting today has been practical, really a way to develop good learners by composing weak learners. So I'm going to address this at the end today. It's really, today it's a member of a family of ensemble algorithms, but it has stronger guarantees than other ensemble algorithms. There is a boosting demo that should be available there. I actually tried it earlier today and wasn't there. So the page was there, but the demo wasn't working. So you can try and see if it's still maintained. I'm going to start by giving an example. And we're going to develop the theory of boosting. There'll be a little bit of theory. You'll have to bear with me. The reason I want to do it is because it's simple. In a couple of slides, we can actually prove everything that one needs to know about the important boosting algorithm. And it's very insightful in terms of some of the key notions that you want to understand in quantifying learning. OK, so what is boosting? So boosting can be viewed in the context of this, in today's terminology, chatbot, right? So this is very popular today. The most famous one until recently used to be this AT&T example, where they had, in the early 90s, developed an automated answering machine, if you want. You call AT&T, and they'll navigate you automatically into the people that should be handling your case. So you would basically say something like, I'd like to place a collect call, and they'll decide what type of need you have, send it to the appropriate person. So, so in the course of working on this system, one key observation was that it's actually very easy to find some rule of thumbs that are often correct, they're precise. For example, if you see the word card in the utterances, you can, with high probability, predict calling card, it's going to be OK. But the coverage is actually very poor. It's hard to find a single highly accurate prediction. So the question for them was, can we put together a lot of simple rule of thumbs in the right way? So the boosting approach to this would be something like this. You'll select a small subset of examples. For each one of them, you'll derive a rule of thumb. Take another set of examples, derive another rule of thumb, and so on. Do this t times, and then combine these rules into one single hypothesis. Now, this seems like a very generic and simple algorithm. The key difficulty is how to do this. I mean, how to choose good sets of examples, how to combine them, and whether, can you say something about whether it's going to work or not? Right? So, so these are some of the questions that we have. OK, so, so boosting is a general method for doing this. it has a specific way of generating the rules, generating the data sets for which the rules actually are going to be good, and combining them in a very specific way. So that's one way to think about boosting today. I want to go back and think about the theoretical motivation. So really, boosting started with a theoretical question, the following theoretical question. So we all know about pack learning. We just finished talking about it, which I'm going to call here strong pack learning. So a strong pack algorithm means that for every distribution, for every epsilon and delta, given polynomially many random examples, one needs to find a hypothesis that has small error, less than epsilon, with high probability, greater than 1 minus delta. That's pack learning. Now, you can have a weak version of pack where you say, same thing, only that my error is not going to be as small as I want, but it's going to be bounded away from a half. So my error is less than a half minus gamma. Okay? So again, I could say I have a weak pack learning algorithm for any distribution, for any delta, for epsilon smaller than a half, I can find a hypothesis with this that has error less than epsilon with high probability. Okay? Clearly weaker requirements, yes?
Why is it 1/2 exactly?
So I'm assuming that I'm doing a binary prediction. So saying a half, we can do easily, right? Getting error half. So the question is, can you be bounded away from a half, right? So that already gives you something if your error is bounded away from a half, but not that strong. Okay, so the question was, and this was a question that was posed by Kearns and Valiance in '88. I don't know if I mentioned kind of the dates here, but really computational learning theory or the pack learning theory started with a very famous paper of Les Valiant in '84, Theory of the Learnable, that started really the area of computational learning theory. So a few years after, actually part of the thesis of Michael Kearns was asking this question. Does weak learnability imply strong learnability? So I'm assuming that, yes, I have a hypothesis class that is weakly pack learnable. Does it mean that it's also strongly pack learnable? Basically, can I boost from weak to strong? And interestingly enough, part of the thesis of Michael Kearns was a proof that indicates or could have indicated that probably the answer is no. And the reason is that he was able to show that if you restrict pack learning to, say, the uniform distribution, not true. So you can have a hypothesis class that is pack learnable on the uniform distribution, weakly pack learnable on the uniform distribution, but not strongly pack learnable. Okay? Everyone understands? Now, in some sense, first of all, it should be clear to you that this does not mean that the general question, does weak learnability imply strong learnability, also has a negative answer. Right? Because we already talked about the fact that for really strong pack learning, distribution free is important. We gave an example that showed that we actually are changing distributions or may want to change distribution when we learn. But this anecdote, if you want, this proof indicated that if one wants to prove this, they will have to go through multiple distributions. Right? They'll have to change the distribution. Because if you start with a distribution and you know that it's weakly learnable there, in general, it will not be strongly learnable there. So you'll have to use the fact that it's weakly learnable on multiple distributions if you want to have a chance to boost it. Okay? And indeed, this is what happened. So Rob Shapiro in '89 gave a first provable boosting algorithm where he showed that you can assume that you have a weak learning algorithm. You're going to call it 3 times on 3 modified distributions, very carefully modified distributions, and you get a slight boost in accuracy. So your epsilon goes down, and you can apply this recursively, and you can get epsilon as small as you want. So that was the beginning of the theory. A year or 2 later, Yoav Freund actually gave another boosting algorithm, different algorithm solving the same problem. And this is where AT&T, I mean, they actually were at AT&T later on, and they tried to actually apply the theoretical boosting algorithm. Didn't work so well. There were several theoretical practical problems that didn't allow them to do it. A few years later, they introduced an algorithm that is called Adaboost. When people say boosting today, they actually mean Adaboost. That had a lot of practical advantages over the previous versions, and this is where kind of the success story of boosting started. Since then, there have been thousands of papers, practical applications, theoretical perspective, and so on of boosting. So that's the history. There are actually some lessons that I like to point out for the graduate students on this, and at least 2 just in this story. So one is a lesson from this place. So Yoav Freund worked on boosting even though he knew that the problem has been solved earlier by Rob Shapiro. So he basically said, I have another idea. I'm going to do it otherwise, and it will be interesting. So good lesson. You know, if someone tells you this problem has been solved already, do something else, not always the case. Sometimes you can still solve the problem differently, bring a lot of insight into a problem, even though someone has already solved one way. The second and perhaps more interesting lesson from your perspective is this paper, the Adaboost paper. It turns out that they tried to publish this paper multiple times, and it got rejected from the main conference in learning theory because people said, well, the problem has been solved already. Eventually, it was published in a smaller conference. I think it was the European Learning Theory Conference, and made a huge splash. So the fact that 3 reviewers thought that not significant enough doesn't mean that it's not significant enough. It was, as history tells us, very, very significant, really important result that had a lot of implications. Okay. So with this as history, we can start talking about Adaboost. Questions? Okay, so what is Adaboost? We start with a training set, as before. We're going to assume that the y's are plus or minus y's, the labels are plus or minus 1, and this is the algorithm, very simple algorithm. So t times, capital T times, we're going to construct a distribution over the examples, 1 to m examples. We're going to call the tth distribution dt. Under this distribution, we're going to find a weak hypothesis, denoted ht. And we're going to find this ht such that it has small error epsilon t on this distribution, right? So when I measure error, the error depends on the distribution, right? It's a weighted count of error. So epsilon t is defined as the probability of over this distribution that ht of xi is different than yi. So I do this, construct a distribution, find a weak hypothesis with small error t times, and then I output a final hypothesis. That's the algorithm. And what we have to do now is we have to be a little bit more concrete and tell you how do we define the distributions and how do we find the final hypothesis and why does it work. Okay, so just a second. Okay, good. Okay, so details. So how do I construct the distribution? I'm starting with a uniform distribution. So D1 of I is 1 over m, uniform distribution. Next, I already have a hypothesis on the previous distribution. On dt, I have ht. I'm going to define dt plus 1, and I'm going to define it in the following way. So dt plus 1 is going to be either dt normalized, we'll see what this constant is later, times e to the minus alpha t, or times e to the plus alpha t. I'm going to do minus alpha t if I predicted correctly on the ith example, and I do plus alpha t if I made a mistake. Okay? And I can write both of them together this way. It's going to be dt of I normalized times e to the minus alpha t times yh of xi. Right? So remember, we've done this a long time ago. So h is plus or minus 1. So h times yi, h of xi times yi, is positive if we did not make a mistake. It's negative if we made a mistake, right? Okay, so zt, as I said, is the normalization. And what is alpha t? So alpha t is this constant. It's a function of my epsilon. So what can you tell me about this alpha t when you look at it this way? Or what can you say about, what do we know about epsilon t? We know that the algorithm, that we can always find a weak learning algorithm. So ht is going to be a weak learning algorithm, which means epsilon t has the property that it's less than a half. If it's less than a half, this is less than a half. This is 1 minus epsilon t is greater than a half. So this ratio is greater than 1. So because this ratio is greater than 1, I know that alpha t is positive. Agreed? It's the ln of something that is greater than 1. So due to the weak learning assumption, I know that this alpha t is greater than half. So what does that mean? Now we can go back to these formulas. That means that example that we predict correctly on these guys, I'm going to demote their weight, right? So I'm going to take their dt of I and multiply it by something that is less than 1. Otherwise, I'm going to promote the weight. I'm going to multiply it by something that is larger than 1. Okay? So that's what I'm doing. I'm taking the example. I have a distribution over the examples. If I got it right, I say, OK, less important for me. I already get it right. I'm going to demote the weight of this example. If I made a mistake on it, I want to promote the weight. I'm going to make this example heavier so that I will have to focus on it next time. If I want to have small error, and this example is heavy, I have to focus on this example. Otherwise, I will not be able to have small error. You see the intuition here? So, so this makes this weighting scheme sensible, right? So, OK, so that's in fact before that. Now, so this gives us the transformation on the distribution. Now let's look at the final hypothesis. Now that we understand this alpha, the final hypothesis is going to be a linear combination of all the hypotheses weighted by alpha. And again, let's look at the relation between alpha and epsilon. Right? So if the error is small, alpha is going to be large, right? Which means that if H has small error, I'm putting larger weight on it in the final hypothesis. If H has high error, I'm putting small weight on it in the final hypothesis, which means that we have a sensible weighting scheme, right? Better hypothesis means larger weight. Okay, so again, these are things that we already, I already highlighted. Now, the final thing I want you to think about is when I've written it this way, I've written t, d of at time t plus 1 as a function of the previous distribution, dt. And you can think about unwrapping everything back to d1, right? So essentially, every step, what will you do? You'll multiply by this e to this term, right? You multiply by e to some term, which means what? You can think about it as, at the end, as e to the sum of all these guys, right? And we're going to go back and revisit this. Okay.
Professor?
Yes.
What would it mean for epsilon t to be 0 if it is possible? Can it be possible?
So then you'll have to think about what does it mean to do ln of 1 over 0, right?
Yes.
What do you want this to be?
Something really small. I mean, consider 1 over 10,000.
No, you want this to be very large, right?
You want alpha to be very large.
Yeah, you want alpha to be large, right? So that's what you'll do, right? So if you have epsilon that is 0, which is not such an interesting case, right, that you already done, but you definitely want to weigh this very high, this hypothesis, right? Okay, the final thing I wanted to say is something about this normalization factor. So we need the ZT, and it turns out that it's very important also in the analysis because we want to have a distribution here. If you think about what is ZT, what we want is that we want to take this expression, sum it over all i's, and get 1, right? It's a probability distribution. I choose ZT such that when I sum this expression over all i's, I get 1. Okay? So if you think about it, that's what you're going to get, right? So ZT is going to be the sum over all I, the sum of dti times this exp, right? Because the sum of this is going to be 1. So I'm just kind of taking the denominator and moving it up. Okay, so that's the algorithm. Before we analyze, I want to run through an example. Yes?
So from a practical standpoint, if we were to implement this as an algorithm, does the distribution here imply that we're, for example, higher distribution for a certain example means that we'll be presenting that example?
Yeah, okay, very good point. So if you want to implement it, so by the way, you can see here that the implementation is trivial. It's essentially 2 lines of code. What you will do is you will change the distribution and sample examples. Next round, you'll sample your example based on this new distribution, right? So if you have a heavy example, you're more likely to see it in the next case. If you have a light example, you may not see it. So the distribution has 2 roles, if you want. One is what's going to be presented to the learning algorithm. That's one. 2, how you're going to measure error, right? Because when you measure error, heavy examples are going to count a lot. Light examples, who cares whether I made a mistake on? And we'll see this in this example now. So here is my data set. So I have a few positive examples and a few negative examples. And this is my D1. All the examples have the same size, uniform distribution. I'm going to learn a weak learner. My weak learner is this vertical line. And this vertical line says it's positive on the left and it's negative on the right. Okay, so I made a mistake on these 3 examples, you see? Which means my error is 0.3. Agreed? 10 examples. And if you do the computation, you'll figure out that alpha is 0.42, step 1. What am I doing now? Now I'm going to reweigh the examples, new distribution. So in D1, I'm going to take these 3 examples and make them bigger because I made a mistake on them. And I'm going to take all the other 7 examples and make them smaller. Hopefully you can see this, that they're smaller. And I'm going to learn again. You don't see it. OK, so these minuses and pluses here are smaller than this. That you can see. Even I can see it. So here is my next weak hypothesis. It's this vertical line. And this vertical line says to the left I'm positive, to the right I'm negative. Again, I made mistakes, this time on these 3 examples. The important thing to note is that I made a mistake on 3 out of 10 examples, but my epsilon now is 0.21. Right? It's not uniform anymore. These were lighter examples. Okay, 0.07 examples instead of 0.1 before. And therefore, now, even though the count is 3, the error is smaller. So, and again, if you compute the alpha, it's bigger, right? You expected it to be bigger. Epsilon smaller, alpha bigger. And that's where I am now. So these 3 examples, these 3 minuses grew. These became smaller. And these 4 that I was consistent on all the times are really small now. OK? I have kind of 3 level of examples now because I'm in the 3rd round. Now my weak hypothesis is this horizontal line, H3. Above is positive, below is negative. Again, 3 mistakes. But this time, epsilon is 0.14. Again, lighter examples, smaller epsilon, alpha is larger. And that's enough. I'm going to stop my Adaboost algorithm and define my final hypothesis. It's going to be a weighted combination of these 3 hypotheses with these alphas, you probably remember. It turns out that this one perfectly classifies the data. OK? So that's Adaboost. Yeah?
What guarantees that error goes down?
Nothing. And that's what we're going to do next. So far, nothing. But I promise it will go down. And we'll see it in a second. Yeah?
So we don't, no matter what distribution of the inputs data, we just assume that the first round is uniformly distributed.
Yes. So we assume that here is a data set. We start with D1 uniform.
And what's the assumption? Like, can we initialize to some other distribution?
Yes. In fact, you can. So you will see in the analysis that it's easy for me to assume that it's 1 over m, each one. If you start otherwise, it will not change a lot.
Then how do we know how many hypotheses we need?
Oh, that's another good question. So we have 2 questions. One is, how do you know that the error is going to go down? 2, how many times do you have to, how many rounds do you have to go? And I'm going to answer these 2 questions in the next couple of slides, provided that the assumption holds. What is the assumption that we're making? The assumption of the weak learnability, right? So the assumption is that every time there is a weak pack learning algorithm, which means you have to remember, for all distributions, I can find a learning algorithm that with high probability, greater than 1 minus delta, is going to give me a hypothesis that has error epsilon. Epsilon is just bounded away from a half, but still. So there is a strong assumption here. As you will see, the strong assumption here is that I can do this for any distribution. And I'm going to use this now to show that what you guys have asked about actually works well. OK, so before that, one important comment. So one cool and important note about Adaboost is that See what happens here. So this guy, the final hypothesis, is perfect. But if I continue to take more weak hypotheses, the weak hypotheses in this case are just vertical lines and horizontal line. They will not be perfect. I can, in principle, keep on choosing weak hypotheses even though my combination is already good. But this will improve my generalization bound. So I can keep on improving and have larger sums here. I will not see it on the training. I'm already perfect on the training. But it will have consequences on what we can do. OK, so let's analyze it and answer this question. So essentially, I'm going to prove a theorem. And you'll see that it's actually simple and interesting to prove this theorem. So I'm going to run Adaboost. My epsilon t is going to be a half minus something positive. So it's bounded away from a half. And I'm claiming that if this is the case, right? So this is my assumption. I always can find a hypothesis with epsilon t that is bounded away from a half. Then my training error is bounded away by this thing. This thing is, think about it, it's a product over all t's of epsilon 1 minus epsilon square root. Now, with a little bit algebra, you can easily see that this is equal to this. Just substitute for epsilon t a half minus gamma t. So you have a half minus gamma t times a half plus gamma t here. So you get this. And this is an inequality that we've seen several times in the last few weeks. OK, let's first do this. So this is the first algebra step here. And this is the second algebra step. Remember that we already said that 1 minus x is less than e to the minus x. My x here is 2 gamma t squared. OK? So I basically did 2 algebra steps. And with these 2 steps, let's see, what does this mean, right? So let's assume for all t, I'm going to find a gamma that is less than all the gamma t's. Now, all of them are positive. I'm going to take the smallest one, and I'm going to call this gamma, right? So I can always do this, right? So just rewriting this guy means that I'm summing here over t times. I'm replacing this gamma t by this gamma, which means that the training error is going to be bounded by e to the minus 2 gamma squared times t. What does that mean? It means that I can make this as small as I want if I take t large enough. Gamma is fixed, positive number. I can make my training error as small as I want. Is it clear that that's what it says? Now comes this question. Why do I state this theorem for the training error? Who cares about the training error? We want generalization error. So why is this OK? An answer? Why is it OK to state it for training? Yeah?
Because the weak algorithm cannot even get the training error on the training set to be 0. So we want an algorithm that can get 0 at least on the training.
OK, so I will get it. But why is this satisfying? Right? So, yeah, I mean, it's not so interesting to be able to minimize error on training. What do you really want?
The weak learners aren't seeing the whole training data, are they?
Say it again?
The weak learners aren't seeing the whole training data.
That's true, or may not see the whole training data. But the final hypothesis is going to, you can evaluate it on the training data. And I'm going to show that it's going to do very well on the training data, right? But why am I happy with doing well on the training data? Where my goal is really, yes?
Because you can bound the risk on the test data by the previous section.
Because of last week, basically. Last week we said we have pack learning now. If you have a bounded size hypothesis space or a small VC dimension, bounded VC dimension, just worry about training. Test is going to be fine, right? And here, what do we have? We have T, capital T, weak learners. So it's a small hypothesis space, parameterized by capital T. If we're doing well on the training, we're going to do well on test, right? So it's enough for us to do this. So the question now is just to prove this. So what do I need to prove? I'm claiming that I just need to prove this inequality because from here all the way to training error is as small as I want is just 2 algebra steps or 3 algebra steps, okay? So I really need to prove this theorem. And let's see if we can do this in 5 minutes or we need to go back next time. Yes?
Just a question on, will we be able to overfit due to Adaboost if we add more and more weak?
Okay, that's actually a good, it's a good question that people have asked in the literature. And there was an assumption, or even today, people think you can not overfit Adaboost. It turns out that you can, and there have been papers that show that, you know, if you really go thousands of rounds, you can overfit also Adaboost. Yeah, so, but it's actually a very good algorithm. Okay, so we want to prove this inequality. And notation, this is my function, right? It's going to be a linear combination of the HTs with coefficient alpha t's. And my h is just the sign of this, right? So h is just plus or minus 1. So the first step I want to argue is that I can write the final distribution. So remember my definition for the final distribution, for the distribution. It was basically here, this expression, dt divided by z times e to this. So I'm just unwrapping this now. And I'm going to get 1 over m for the first time. And then product of all these components, product of e to this guy, which means it's e to the sum, yi went outside, divided by the product of all these zt's, right? So this is directly from the unwrapping of the definition of the distribution. And here I'm just rewriting this. Right? This is by definition the way I've written it here. This is just f. Okay? So I unwrap the probability distribution. Okay, step 2, I want to argue that the training error is less than the product of all the normalization constants. So again, one thing that I want you to agree with is that because if I made a mistake, it's another way of saying that y times f of x is negative, right? The sign of y and the sign of f of x is different, so the product is negative, which means that this is greater than 1. E to this is greater than 1. OK, now let's compute what's the training error. What is the training error? By definition, the training error is count 1 if I made a mistake, count 0 otherwise, divide by m. OK? That's the definition of error. Everyone agrees? This is really what I want you to take from this proof. I want you to see all the ways we can define errors and play with these terms, right? So you have to convince yourself that what I'm saying here makes sense. So I'm arguing that this is the definition of error. Now, notice that when I'm summing this, I'm summing for all these cases 1. Instead of 1, I'm going to replace it by this guy, because I know that when I made mistakes, this is greater than 1. So this is less than 1 over m when I'm replacing all the 1s by this guy. OK? Now, what is this? If we go to the previous slide and see our definition of the distribution, move this denominator here. Remember, move this to this. And now let's look at the next slide. That means that the error is less than the sum of this. And I'm arguing that this is, OK, let's just, this is just step 1 that I showed you in the previous slide. And why is this equal? Because this sum has to be 1, right? It's a probability distribution. OK. Almost done. OK, so these are just explanation of what we've done, right? So this is the last step. Final step, I'm going to show that the normalization factor is actually this factor that is related to the error this way. So square root epsilon t1 minus epsilon t. So let's compute what is zt. So again, zt, if you remember, was the normalization factor, which means that if I take my definition of the probability distribution summing over all I get 1. So I showed you in the previous slide that this actually means sum over all I dt of I times this. This is really just the definition of normalization. Now, the way I'm going to think about this sum is in 2 components. I'm going to think about summing all those examples on which I made a mistake, and then summing all those examples on which I did not make mistakes. OK? So splitting the sum to mistakes and no mistakes. Now, by the definition of epsilon t, if you go back to the slide that showed the definition, this really is just epsilon t e to the alpha t. This is just the error. And this is all the cases where I did not make a mistake. So it's 1 minus epsilon t times e to the minus alpha t. And again, if you go back to the definition of alpha t and substitute, you'll get this. So this step is just algebra. So what I want you to go and look at again is the definition and really understand the different ways we're writing errors here, which will be quite insightful. Essentially, steps 2 and 3 together prove the theorem. And what we've shown is that under the assumption of you have a weak learner, we can show that Adaboost hypothesis will have training error as small as you want as a function of t, capital T. OK, so let's stop here. We're going to pick this up on Thursday. And I want to remind you that when you plan your time, on Thursday at 6, we're going to have another lecture devoted to the midterm. OK.